Oh, hello. And this time we're going to look at something a bit different, not ETCS, but TPWS. And we're going to have a look at how TPWS loop positions are currently established and the calculator tool that is used by many designers to place the TPWS overspeed sensor loops. So many signal designers on Network Rail or working for Network Rail will be familiar with the calculator tool, where information about the line speed, gradient, safe overrun distance can be entered, and the various buttons can be clicked in order to generate a design for the overspeed sensors. And we're going to have a look at logic behind this tool, some of the history of TPWS, some of the issues that need to be considered when designing a TPWS installation. And we'll also look at some of the limitations. So what about TPWS? Well, there was a number of issues where drivers were passing signals at danger and getting to the point of a conflict. And so people were considering the risk of overruns. And they were looking for systems to manage that risk, to intervene in the event that the driver was failing to respond to the cautionary or red signals. Automatic train protection is the obvious answer. However, it can be expensive, and until all of the trains are fitted and all the signals are fitted, you don't get any benefit or significant benefit. For TPWS, the train-borne system reads signals which are sent as frequencies from loops mounted between the rails. The system on board can interpret the sequence and timing of those frequencies, either to decide that it is a train stop command that is being transmitted, in which case the brakes will be applied immediately, or to test the speed of the train and confirm it is below the set speed of the loops. Signals received in an invalid sequence, so for instance, if you're going the wrong way on a bidirectional line, do not generate a reaction. Now, the fact that the frequencies are transmitted by loops mounted on the track means that the system is not fail-safe. Unless the onboard receives both of the frequencies, no reaction will be generated. So the operation of the trackside transmitter and then the loop impedance for the cable and the actual transmitter loop need to be monitored in order to detect if the system is working. And if the associated signal is red and the trackside TPWS equipment cannot be detected as operational, then the signal in rear will also be held at red. So that gives a measure of protection. Obviously, there is a short window of opportunity where the train will have passed the preceding signal, where the loop could fail or the transmitter could fail. However, this is only a small time window, and one has to remember that most trains approach red signals with the driver in proper control, preparing to stop, and so the TPWS is not required. It would be a Swiss cheese type situation where the train was not going to stop at the red and the TPWS failed after the train passed the preceding signal. So what is TPWS? Well, it's not designed to prevent SPADs, that's signals passed at danger. That is still the driver's responsibility. What it does do, though, is to seek to stop a train exceeding the safe overrun distance, often called the SOD. That SOD is normally the overlap, but it can be longer depending on where the first conflict is. It should not impact the performance of the train service. The idea that this system is sitting in the background, just monitoring things and only intervening when it is absolutely necessary. Now, whilst it was designed to manage SPADs, it can, with limitations, and perhaps I might do another video in due course about those limitations, it can monitor significant reductions in permissible speed. And it also has been extended to manage the impact speed at buffer stops. So the system was developed and it had to be developed quickly and deployed quickly because the risk was out there, accidents were occurring. So TPWS was designed so that for each train fitted and each signal fitted, the safety of the system was incrementally improved. You did not have to wait for the whole fleet or the whole railway to be fitted, as we might need to do with ATP. Now, it was accepted right from the beginning that it could not give the same level of protection as automatic train protection or an ATP system. It was only an intermittent transmission system with intermittent supervision. ATP normally has continuous supervision and may also have continuous transmission. The application rules were established to give a quick, cost-effective deployment which could be undertaken by medium-skilled designers using a set of rules. There were some compromises in those rules, but the vast majority of the risk was managed. So some of the early assumptions. Well, one of the assumptions was that drivers will normally brake for a red signal pretty evenly at a braking rate of about 6% of gravity, or G, and that's roughly equivalent to the traditional step 2 brake. So this is based on the fact that drivers see a cautionary aspect and their normal reaction is to start braking, and they will brake gently, hoping that by the time they get to the red, it is no longer red. And this was reinforced by professional driving standards being introduced. Often they were called defensive driving for when they were initially introduced, but they're now professional driving standards. It was also assumed that drivers will obey any speed restrictions. So whilst drivers might fail to recognise the need to brake for a red signal, because of their familiarity with the route, it is almost an automatic reaction to manage speed restrictions and brake for them. It is an assumption, and one has to be aware of that. The rules also assumed that one would have a standard overlap at each signal, so any point of collision would be at least 180 meters from the signal. And it was also assumed that the emergency brakes on a passenger train would be able to achieve 12% G, and on a freight train, 7.5% G. Now, at the time TPWS was introduced, this was the case for some modern stock. However, much of the heritage stock could not achieve those brake rates. However, it was a good assumption and one which has proved to be very valid. However, as we go on, we will learn that there were also then considerations for those trains that could not achieve those brake rates. So the original design process was to establish whether a particular signal qualified for fitment, and a flowchart was produced with a number of inclusion and exclusion codes. And principally the questions were, is the train on a is the signal on a passenger line? Are there conflicts in the route or in the overlap ahead? And is there a realizable collision in that route or overlap ahead? So exclusions covered things like emergency crossovers or points which were locked out of use. It excluded purely shunting activities, and there were other exclusions around absolute block, etc. It wasn't a perfect exclusion or inclusion process, but it was designed to make the system economical because money is always tight, but we want to improve the safety of the railway. So once it was established that fitment was required, the first thing is that a train stop sensor is placed at the signal. The train stop sensor consists of two loops, energized when the signal is at red, transmitting two different frequencies, and when the train reads the first frequency and then at the same time reads the second frequency, it will apply the brakes. It then looked to see whether an overspeed sensor was also required. Was the safe overrun distance, the SOD, sufficient that a train approaching at the permitted speed would actually stop if it was tripped at the signal before it reached the point of conflict? This often can occur, particularly if the reason for the fitment is because the points are in the overlap of the next signal. Also, are the signal controls for any of the points in the overlap ahead, for instance, flashing aspects, delayed clearance? That might affect whether you need an overspeed sensor because the driver is getting other information to reduce the likelihood that they will SPAD. And also, do trains normally start from rest? So platform starting signals in a terminal station don't need to be fitted with an overspeed sensor. So the original placement process was to establish the attainable speed on the line, and this required looking back a distance from the signal to make sure that speed reductions and things were taken account of. Also, speed increases needed to be considered. If a line speed on approach might be 70 mile an hour, but if 200 meters away a 30 mile an hour speed restriction ended, then the attainable speed is probably going to be closer to 30 than 70. So having established that attainable speed, a table can be used to identify the distance between the OSS trigger loop and the signal, the top right. And that OSS could then be adjusted in position to take account of gradient and if there were conflicts with other track-mounted equipment. Having established the distance between the trigger loop and the signal, then the distance between the two loops could be established using the second table. And this distance then generated what was called the set speed. So this was the speed at which a passenger train or a freight train would be able to travel without being subject to a trip. And these set speeds were set to avoid nuisance trips based on the fact that the driver would brake from the first caution and would brake steadily towards the red. So what are some of the limitations? Well, in the early deployment, the furthest an OSS would be placed from the signal was 350 meters. And what that meant was that the highest approach speed that could be protected was about 70 miles per hour. So if we look at this braking curve here shown for a train capable of achieving 12% G, the zero line axis on the vertical is where the signal is. And you can see that if a train passes that signal at just over 40 miles per hour and is tripped by the TSS, it should stop just within the overlap, 180 meters beyond the signal. If we go back 350 meters on approach to that signal, we can see that the blue line is roughly at the 70 to 75 mile per hour point. The other problem is that when we did place a loop at the 350 meter point with its set speed would actually mean that if a train or the driver, probably more to the point, just got under that set speed and then continued at the same speed, they would actually be tripped at the signal faster than the TSS was effective. Also, if a driver did accelerate after passing a loop, then that could also give a gap in the protection. One solution to deal with that 70 mile per hour situation was to place an extra OSS called a TPWS plus at 750 meters from the signal. And this would give a theoretical protection up to about 100 miles per hour. And we can see the arrangement of the loops for both the TSS, the OSS, and the OSS plus or TPWS plus loop. So what about freight and passenger trains? Now we know that freight and passenger trains brake at different rates, but the OSS transmitter loops are fixed distance apart. So to counter this, the onboard is set to have two different timing settings. For passenger trains, the setting is 974 milliseconds, but for freight it is 1218 milliseconds. When the train passes over the first active loop, the arming loop, the timer is started. And if it expires before the second loop is read, then the speed is low enough and no reaction will occur. However, if the second loop is read before the timer has expired, then an overspeed trip is initiated. And what that results in is that the trip speed for any pair of loops is about 80% for freight of the passenger speed. And that then reflects the fact that the freight train will take longer to stop. Whilst this is not perfect, it is a good management of risk, particularly since historically freight trains had not been driven hard at red signals and had significant SPADs. So the whole idea was to provide an effective and economic provision. And it was felt by the industry that the original deployment rules, later enhanced by TPWS, gave a good level of protection. And they were aimed at reducing the likelihood of serious consequences for a SPAD caused by a driver failing to brake at all or misjudging the braking. And estimates at the time were that it reduced the overall risk of collision following SPAD by about 80%. And that was a good amount of risk taken out of the industry. And it should be noted that even if a train did SPAD and get to the point of collision, it would be at a much lower speed than if TPWS was not provided. In parallel with the development of TPWS, people were trying to understand the risk of overruns, what caused them, and what the risks were when they did occur. The overrun risk process looked at designing junctions in the safest way possible. Rather than having multiple conflicts just behind signals, was it possible to reposition the signals, or was it possible to design the junctions so that any overruns were diverted away from conflicts? A tool called the VariSPAD tool allowed the operators and designers to consider the likelihood of a SPAD, taking each signal individually, looking at how often it might be at red or green, where it was, whether there were sighting issues, how long the overlap was, other distractions on the approach, and etc. And that supported a subjective decision process on whether the residual risk was tolerable. And this started well. However, as people started to look at TPWS, they began to go down the rabbit hole of accuracy, trying to evaluate the residual risk to 2 or 3 decimal points. And so we began to have debates with the various train operators about absolute protection. Would they accept residual risk? And the answer was no, that caused challenges for them. If there was a potential to reduce the risk further, then they felt that it should be done, even though it would not be them paying for the extra equipment. And then what about trains which did not meet the theoretical braking performance, so the 12% G for a passenger train? And here there was more politics, where trains were declared to not have a high emergency brake rate, even though it was known that in normal service they could easily achieve 12 or even higher percent braking. And this was because rheostatic and regenerative braking would be switched off in an emergency. And so there were many debates in these meetings about whether a calculated stopping distance, which was 1 meter, 5 meters, or 10 meters over the available distance, was safe enough or not. And if the stopping distance was, say, 10 meters over, then it would be probably a definite no. But when you get down to 1 or 2 meters, then people were arguing about whether there could be a small adjustment of the TPWS loops or the overlap length in order to make it safer. which was all a bit silly, really, when loops can be moved by up to 12 meters in part of the design process and installation process. The actual antenna on the train was not at the front of the train, that the brake build-up times and the brake actuation times could vary, uh, and various other parts of the system could be at fault. But it was a case of covering my arse, and uh, train operators would not accept risk from the infrastructure manager. So one of the solutions was to apply conditional double red. So on higher speed lines, or where the TPWS protection was not considered to be adequate, then CDR, or conditional double red, can be provided. The inner signal, that's the one protecting the conflict, is provided with TPWS as normal. But because that TPWS is not effective on its own, the preceding or outer signal is held at red until either the inner signal is showing proceed or the train has passed over the TPWS OSS for that outer signal. So we know that either it has been tripped or it is going at a low enough speed that the inner signal protection should be effective. Now, of course, it doesn't take account of the fact that having seen the outer signal clear, the driver may accelerate, but that is a risk one has to tolerate. CDR had a mixed popularity with drivers and operators. There were long debates about whether they improved or the performance or had a negative impact. If the inner signal was red and was going to remain red, then braking early by the outer signal being held at red until the train approaches is not going to make any difference. If, however, the inner signal is going to clear after the outer signal has been passed, then the approach may be slightly slower. However, if the signal doesn't clear until the train is on the approach to the inner signal, because the train has slowed earlier, it will get there a little later and it may still be rolling and therefore will have a better throughput. It was all very complicated, argumentative, and a lot of opinions. So if we have a look at CDR, we have got two signals, the inner signal on the left, protecting the junction, the outer signal on the right, and both signals are red. So we've got the TSS indicated in red loops at the two signals energized, and we've got the OSS indicated in orange on the approach to each signal energized. As our train proceeds, it passes over the outer signal OSS, and providing it's going slow enough, no reaction will occur. Using train detection, the train can be detected having passed that loop, allowing the outer signal to clear to yellow and disabling the TSS at that signal. So our train can now proceed to the inner signal and it will be monitored by the OSS for that inner signal. And if it does SPAD, then the TSS at the inner signal would operate. If, however, before the train arrives, the inner signal clears, then the clearance of that signal will turn off the power to the TPWS for the inner signal and enable the outer signal to clear, which will then turn off its TPWS. Now, one of the issues was trying to understand how likely SPADs were and also how likely it was that any particular train that did SPAD would reach a point of conflict. And we always know that if something can go wrong, it will go wrong at some point. However, we're looking at a large number of trains and a large number of approaches to a red signal. And thankfully, SPADs do not occur that often. We are grateful that the drivers are generally conscientious. Many of the SPADs that do occur are actually only minor misjudgments of braking and result in an overrun distance of a few meters. And it was found by looking at historic information that it was very rare for a driver not to respond at all. On higher speed lines, the signalling tends to be four aspect. So at the double yellow, the driver will receive an AWS horn, which has to be acknowledged. at the single yellow, an AWS horn that has to be acknowledged. And unless the driver has been running on continuous double yellows for some time, which can be condition people to not respond, then it's unlikely the driver won't respond at all. What we did notice, though, that sometimes drivers did respond to the first caution, begin to reduce the speed, but then would get distracted or might know that they have got a significant distance to travel before they need to brake. If one looks at the accident that occurred at Salisbury, from reading the accident report, it appears that the driver did see the first caution. However, knowing that that was a very long distance from the red signal, and knowing that normally they didn't need to brake until a later point, they continued at a higher speed, looking for that braking trigger, which they then missed. And when they did realise they needed to brake, it was too late, and a SPAD occurred, and unfortunately led to a collision. So working with RSSB, Network Rail decided to try a different approach. Could they use historic SPAD data to predict the speed of the train on the approach to a red signal and passing it in if it was going to pass it? So for each potential speed, the likelihood of a SPAD and it reaching the point of that conflict could then be calculated. And that would enable the overall effectiveness of the TPWS for a particular type of train to be assessed. And if you had multiple types of trains, they could all be reviewed individually and then an overall effectiveness calculated based on the train service. So let's just have a think about this. So we've got a railway, we've got a signal protecting a conflict beyond the overlap, it's got a TSS and it's got an OSS. And if we look at the location of the OSS, then looking at historic data, we could see that the speed the train would pass the OSS position was a curve, roughly a normal curve, with a probability of the train going very slowly being small, most trains travelling at around about the 5 or 6% braking curve to the red signal, drivers having reacted early, a few trains going a little bit faster, and just a few trains going fast enough to exceed the OSS set speed. Or in this case, they also need to consider that a few would exceed line speed. Moving to the right, we can see that for the signal, the speed that a train passes at when spadding is likely to be very low, if at all, and hopefully it doesn't pass it at all. But as the speed increases of the SPAD, the probability gets much lower. And we can cap what we're interested in using the set speed of the OSS. So we now are only interested in the likelihood of a train exceeding line speed at the OSS or exceeding the set speed of the OSS at the signal. And from all of that, we can calculate a probability of where a train will stop based on an intervention occurring for either reason. And that probability curve shows that most trains will stop on the approach to the red signal, but a few may go past. But the further past the signal, the lower the probability. And if we now establish where the safe overrun distance is, then the effectiveness of the TPWS in managing particular SPADs is the area under the probability curve up to that solid position. And that can be calculated for each of the individual trains and then added together for the train service. And that was what a tool produced by RSSB was designed to do. It allowed one to put in details of different types of trains. You could put in details of the TPWS installation. You could put in how many of each type of train would approach the signal, and it would calculate for you for each signal the effectiveness of the TPWS based on that train service. So we can see for the top signal here, There are 10 train type 4s would approach and 20 train type 8s, and the overall effectiveness was evaluated to 86.6%. The third and fourth ones you can see are evaluated to 95% because it was decided that one would never claim more than 95% effectiveness. So how do you design the TPWS fitment to give that best effectiveness? Well, this is where the calculator tool came in. The rules were good, but they had the opportunity to do better, particularly if you wanted to take account of types of train, as the effectiveness calculator was doing. And we still wanted the design to be proportionate to the risk being experienced on the railways. And so the logic became quite complex, and it was much easier to use a tool which could be adjusted quickly by the designer to see how the loops should be placed. And by enabling us to efficiently deploy TPWS and keep its cost down, it actually allowed more fitments. So the rules became that all main signals or stop boards on passenger lines which protected a conflict would be fitted. They would protect on converging lines. They would protect where the overlap of the signal ahead contains a point of conflict. And that was both on freight lines and on passenger lines, particularly where the point of conflict was actually on the passenger line. Limits of shunt were also provided with basic protection on passenger lines. There were a number of locations where bidirectional moves were allowed, and if there was a stopboard or signal limiting those moves, perhaps to go into a wrong direction platform in order to reverse, then those signals could also be fitted. And some level crossings also generated fitment based on assessment of the risk for that level crossing. So what was the logic? Well, the first thing was to establish the maximum speed at which the intervention by the TSS would stop the particular train within the SOD. And if that speed is less than the maximum approach speed, then you need to place an OSS with the effective speed as the set speed, so that you can't approach the TSS without accelerating at higher than the TSS effective speed. You then repeat the process to establish the maximum speed for which an OSS intervention would still stop the train within the SOD. And you'd repeat 2 and 3 as necessary until either one has reached the line speed or a limit of 3 OSS loops has been provided. And how do we move on to improve effectiveness? Well, we've established a base number of loops that we need to provide, so that effectively controls our expenditure. We can repeat the placement process for trains with longer braking distances or lower percentage G, using that same number of loops. And we can establish whether that base number of loops can be effective for each of the different types of train. That enables us to choose an effective design based on the different train types so that we can give the most protection to trains which can't achieve 12% G. We can then look at the history of SPADs to be confident to move the furthest out OSS closer to the signal, whilst of course keeping it in the effective band. And if there are more than one OSS, we can move the other OSSs in close to the signal, because we discovered that the highest likelihood of a SPAD occurring is with a driver who has begun to brake and then misjudged the braking or released the brake because they think that they will stop in time, or perhaps have been distracted. So that logic took quite a while to develop and was found to be quite complicated for people to apply and not always intuitive. And hence we moved on to the tool. So now we'll look at the tool in action. So here is the calculator on the screen. It's an Excel program with an Excel spreadsheet where you can put in the inputs and get the And behind the scenes, there is VBA code which does all the work. So let's have a look. Top left, you'll see there are some yellow boxes, and in there we can put the line speed for passenger trains. So let's start with uh, a 90 mile an hour approach. Freight trains, well, traditionally they would go up to about 60, but now some of them can go up to 75. So let's put that in. The gradient, we'll just leave it as 0. Obviously, you need to think about the falling and rising gradient on the approach to the red signal in the TPWS. So typically going back about half a mile. Safe overrun distance, well, 180 meters is an overlap, but quite often it'll be about 220, let's say that. So we've now input the information, and we can put our signal identity in as well. Test. There we go. And now we are ready to get the spreadsheet to work for us. And as you'll see down the middle of the screen, there are some buttons and there are also some steps. So we've done the step 1, entering the details. So now we can press the Apply Rules button. And the program gives us some feedback as to what it's been doing. And the first thing it's tried to do is to place the loops based on a passenger train with 12% G. So that's column 2. And as we can see, it's actually managed to do it using an OSS and an OSS Plus, and it seems to be happy with those. So if we click OK, it'll now go and try the column 3, a passenger train with a 9% G, and in this instance, it hasn't been able to solve that with the same number of loops. It's going to check for column 4 just to be sure. And it's now got the loops being placed for the best rate that worked, which was based on the 12% G. And it's now adjusting things. It's moving the outermost loop in a little bit closer in, because we know that trains don't tend to approach at the line speed. They tend to approach somewhat lower than that. And it's then that the driver gets distracted and doesn't brake. And a little bit of adjustment of the middle loops, and we now have a solution. So our solution is to have a TSS, and that will be effective for 12% G. We've got two OSSs, one at 200 meters with a set speed of 34.5 and another at 600 meters with a set speed of 62. And we can see that that works for the passenger 12%, that's green. For the others, it is not an acceptable solution. However, what we can also look at is what speed the loops are effective for. So, for instance, any train up to 40 miles an hour with a 9% G, that's the cell over here, will be protected if it's up to 40 miles an hour. And similarly for OSS1, if it's up to 57, and up to 81 mile per hour for the OSS2. So then it's unlikely that a train's going to be doing more than 80 on a 90 mile an hour line if the driver has responded at all. And we can also look at the effective speeds for passenger. Now, what else can we do? Well, one of the things we can do is to look at what happens if we emphasize freight. Now, this may not work with this setting. We'll try it, but we'll try clicking the step 3, the freight bias. And it's now looking at whether a solution can be found in freight. And the answer is no. It has used up 3 loops and it can't achieve that, which means that it will fail. And it will just keep going through the other tests, placing the loops. And the end result is that it doesn't work for TPWS, for freight trains. However, it still works for the passenger trains, which is good news. The other thing we can do is we can add a loop. So if we decided that although it was two loops, we really wanted to try and protect the 9% G passenger, we could try the add a loop. I should have gone back, and it's now trying to add a loop on the freight, which it will not achieve, so that's my mistake. So let's just do the rules first for the passenger train. So you can see it doesn't take long to do these. So we've got a solution for the passenger. Now let's try adding a loop. So we apply the passenger rules first. So you can see it redoes those. And then it adds a loop because we've got a third one available. And it then works through columns 2 and 3 and 4. And now we've discovered that here we can actually manage to get protection in column 3 for a 9% G using that extra loop. And we can now tweak the loops a little bit, and we have a solution here now where a 9% G train is protected. Worst case overrun is 207 meters. So that's quite a good solution. We can also do things like look at what happens if we do change the line speeds. Perhaps if we drop the freight speed to 65 and we perhaps increase the safe overrun distance because we move the signals a little bit. Let's make it 250. Now if we apply the rules, we have a little bit better situation and the freight is nearly protected, but we would probably need to extend the solder even more. So we can actually try different scenarios and see what would happen. So that's the tool. It really works itself quite well. And of course, being signal designers, sometimes we like to actually change things or move something. So for instance, we might decide that OSS 1, we have to put it at 200 meters, perhaps there's a bridge in the way. So we can do that and we can then recalculate and it will tell us what the answers are with that. So we can actually design our own bespoke fitment if we wish. Anyway, there we go. That's the calculator. I hope you found using it simple and easy, and hope you enjoyed this short video. Thank you very much for listening.